Good afternoon. I welcome to this session of IC engine gas turbine, and today we will continue our discussion on engine operation, and we will try to see how the engine operation can be classified into three different zones. So, that means we can classify entire engine operation into three distinct zones, that is idling zone, cruising zone and the power zones. Now, we need to know that why we can classify, rather by how we can classify this the entire engine operation into three different zones. If we try to recall that the fuel air ratio that is supplied into the engine cylinder, if it is a 4-stroke engine, 4-stroke SI engine, then of course fuel and air mixture will be supplied through the carburetor. But if it is 4-stroke CI engine, then only the air will be supplied into the engine cylinder during the intake stroke, and then fuel will be injected into the cylinder through a fuel nozzle. Now, of course, when we talk about carbureted engine, then the fuel air mixture, that is fuel air ratio, is supplied into the engine cylinder, and depending upon the fuel air mixture, I mean fuel air ratio which you are supplying into the engine cylinder, that fuel air ratio is a stoichiometric fuel air ratio, keeping in mind that engine should run in its design condition. That means what I would like to say, depending upon the load which is demanded from the engine, the fuel air ratio which is being supplied into the engine cylinder needs to should vary. So, that means it is not required to supply a constant fuel air ratio all times irrespective of the loads of the engine. So, engine should run at different loads, and at different loads the amount of fuel and air mixture, the rather fuel air ratio or air fuel ratio to be supplied into the engine cylinder will vary. So, we should know in the amount of fuel air ratio required to run engine, rather how we can classify, how we can distinguish different engines or the entire engine operations into three different zones depending upon the requirement of the fuel air ratio. Rather, depending upon the zone in which the engine is running, the amount of fuel air ratio will vary, and that is what we should discuss today. So, in the internal combustion engine can be as I said you that entire operation. So, operation of IC engine. So, this operation of the internal combustion engine can be classified into three different categories, So, entire engine operation can be categorized into three different zones. One is idling, number 2 is cruising zone, and number 4 is power zone. So, now we need to know what do you mean by idling, what do you mean by cruising, and what is the power zone. So, this is cruising zone, this is idling zone, and this is power zone. So, as I said that means we can divide the entire operation of the internal combustion engines into these three different zones. That means depending upon the load, engine should run whether it is running in idling condition or whether it is running in cruising zone or whether it is running in power zone. That will be the load that will be defined by the load which is extracted from the engine. So, the load, the power developed by the engine, the power required from the engine, we need to know what is the power required, what is the power should be developed by the engine. So, depending upon the power which is required from the engine, we can say that now engine should run in this zone. So, if we say the requirement of power from the engine is not very high, then we can say the engine is running in this zone. If it is an intermediate load, load, then we can say the engine is running in this zone. And if the power, output power or the power developed by the engine is so high, that means of course the load demanded by the engine is very high, then the engine should run in this zone. So, these 3 zones are basically defined based on the load at which engine is running. So, I am writing these 3 zones are defined based on the load at which engine is running, right. So, I can write, so first that is the idling zone. So, what do you mean by this? That again if I try to recall this engine, so this is a carburetor. If we talk about carbureted engine, so this is fuel, this is air. Now, so this is throttle valve. Now, so this is engine cylinder and this is the this is BDC, this is TDC, this is carbureted and this is the throttle valve. And this is intake valve, this is exhaust valve, and this engine is running like this, and we have spark plug if we record. So, now question is, when throttle valve is almost closed, that means it is fully throttle condition, almost closed, and but I cannot say the fully, totally closed. So, almost closed but not fully. So, idling zone, which is defined, as I said that if I go back to my previous slide, that 3 zones are defined based on the load at which engine is running. So, idling zone is zone in which engine is running, but no load is demanded from the engine. Now, so that means engine is running, starting, but no load is we are not demanding any load from the engine. So, that means the throttle valve is almost close but not fully, that means engine is still running but supplying no load. So, engine is still running, startup condition, engine is still running, supplying no load. So, throttle valve is almost closed but not fully. So, in that zone, what will be the requirement of fuel air ratio, that is very important, that we should know. So, maybe what we can say, that since we are not taking any load from the engines, so maybe the fuel air ratio that will be supplied to the engine is it is not expected that it is quite expected that the fuel air ratio that will be supplied during this zone of operation will not be very high, but that is not the case, that we will discuss today. Now, next is, that is very important, cruising zone. Cruising zone, engine will operate most of the time at cruising zone. So, this is the cruising zone, most of the time engine should operate in this cruising zone. And what about the power zone? Power zone is what is a power zone? That means, you know, in this zone, this I mean this in this zone, now I can say the high power engine needs to supply maximum power. So, that means idling zone, cruising zone and power zone. So, you can see that depending upon the load which will be supplied by the engine, we can classify these three different zones. And now we need to know what will be the amount of fuel air ratio, I mean what will be the amount of fuel air or air fuel ratio to be supplied to the engine if the engine is running in idling zone, or if the engine is running in the cruising zone, or if the engine is running in the power zone. So, depending upon the zones, I mean zone of operation, the amount of fuel air ratio that will be supplied to the engine will vary. So, now I can draw one figure schematic that is very important, that so if we try to write schematic, so that is the fuel air ratio. Now, we know when we talk about a particular air fuel ratio particular engine, so for that I know what is the stoichiometric air fuel ratio. So, this is the fuel air stoichiometric. So, I can write fuel air stoichiometric. Now, this is percentage opening, percentage of throttle opening, see percentage of throttle opening is directly related to the load. So, as I said that if we can recall that when we need to supply maximum load, of course, it will be to fully open, and we have seen during idling zone engine is running but supplying no load. So, throttle valve is almost closed but not fully. So, this throttle opening, or I can say this is load. So, this is along x axis, and if we try to so this is the case. Now, this is we can classify and then so this is 100%, this is 80%, this is 20%, this is 5%. So, it is not fully closed. So, 5% is still, I mean 5% is open. So, this is if I try to label this is the characteristics curve of the engine operation. So, A, B, then C and then D. So, if I write that, so A to B, this is basically, so this is the idling zone, and then 20 to 80, this is cruising zone, and 80 to 30 this is power zone. So, what we can see that at A B, that is 5 to 20%, I mean this is the 5% to 20%, this is the idling zone. That means this point A, this is, if we try to recall, this is no 0%, since this is not 0%, because engine is running, but the throttle valve is almost closed, but not fully. So, we cannot say this is 0%. So, see, what we can see from this figure is that during idling zone, when throttle valve is remaining almost 5% to 20%, this is not, I mean closed, but almost closed. So, we can see that the amount of fuel air ratio that will be supplied to the engine, which is larger than the stoichiometric one. We will discuss, because as I said that it is quite expected that since we are not supplying any power from the, we are not supplying no power, no load from the engine, but still we need to supply higher amount of fuel air ratio to the engine. Why we need to supply, that we should know. B to C, that is 20% to 80%, that is cruising zone. This is cruising zone. Most of the time engine operates in this region, in this zone, that we can see from the figure as well, that the supplied fuel air ratio to the engine is the stoichiometric one, that is as if the engine is running at its designed load. That means we need not to supply fuel air ratio which is either lower than the stoichiometric or higher than the stoichiometric. Of course, always you need to supply fuel air ratio will be higher than the stoichiometric, but this is the zone where most of the time, that is why 20 to 80% throttle valve is open, and this is the I can say most economic condition, economy state of the engine operation, because we need to supply the air fuel ratio that is stoichiometric one, chemically correct one. Finally, we can see that C2D, that is throttle valve is 80% to 100%. That means it is almost, I mean not almost, is fully open. When it is 85% almost fully open, 100% fully open, and in this condition throttle valve is fully open, that means engine needs to supply maximum power, maximum load, and for that of course again if we try to extract more load from the engine, we have to supply more input energy, because we are trying to maximize the power output. So, it is our expectation that we should supply more input energy, and for that of course we need to supply higher fuel air ratio, and that fuel air ratio will be again higher than the stoichiometric, that is clearly seen from the schematic. So, supply of more fuel air ratio, that is higher fuel air ratio than the stoichiometric one during power zone is justified, because we are trying to maximize the power output, and for that we have to increase the input energy. But during the idling zone, we can see that the supply amount of the amount of fuel air ratio that should be supplied into the engine cylinder is even higher than that which is required for during the power zone. And why we need to supply the higher amount of fuel air ratio which is greater than stoichiometric, that is true, and also the amount of fuel air ratio required for the operation of engine in the idling zone is greater than that required to operate the engine in the power zone. So, now at least we should know why we need to supply higher amount of fuel air ratio during the idling zone. So, just I will try to explain now that and for that again we need to draw the schematic. So, if we try to draw the schematic, this is carburetor and this is a fuel and this is air, this is carburetor, and so this is exhaust valve, this is combustion product, and this is throttle valve. So, this is throttle valve and pressure is near about 4 psi, I can write 4 psi, and at the exhaust pressure is 14.7 psi, right. And this is also, I mean this is also 15 psi. So, this is intake valve. Now, as I said that during idling condition, why? So, first question is why fuel air ratio is supplied to the engine during idling zone is higher than the stoichiometric air fuel ratio, than the fuel air stoichiometric ratio. So, if we now look at the schematic carefully, what is done? So, what I said that during idling stroke throttle valve is almost closed, almost I mean 5% to 20% opening. Now, when exhaust valve is closed and during intake stroke intake valve opens and piston travels from TDC to BDC. So, this is bottom dead center and this is top dead center. Now, what will happen when piston travels from TDC to BDC during intake stroke and throttle valve open partially, very small amount of very small opening is there and intake valve opens. Now, I mean from previous exhaust stroke the clearance volume that is indicated by this is the clearance volume. So, at the end of the exhaust stroke exhaust valve closes and the some amount of combustion product will be there in the clearance volume and the pressure, the combustion gas pressure will be 15 psi that I have indicated in the schematic. Now, question is when the next stroke is in next cycle, that is this first stroke of the next cycle, that is the intake stroke. Now, when that means that now what we can say, the gas pressure in the clearance volume that is 15 psi and that gas will be there in the clearance volume from the previous exhaust stroke. Now, this gas cannot be removed from the clearance volume and the gas pressure is 15 psi. Next first stroke of the next cycle is the intake stroke. Piston now travels from TDC to BDC. Now, because of this travel, as the throttle valve partially opened and near the throttle valve pressure is 4 psi, because across the throttle valve there will be a huge pressure difference. Upstream of the throttle valve pressure will be atmospheric pressure, downstream will be 4 psi. That is what is important, because we need to create negative pressure, and during exhaust stroke intake valve was fully closed and the pressure just downstream of the intake valve will be 4 psi. Now, the moment when piston start traveling from TDC to BDC and intake valve opens, the combustion gas pressure that is there in the clearance volume will try to rush towards the throttle valve, because throttle valve is now creating a huge pressure difference between across this valve, and the gas pressure is 4 psi. So, what will happen, we are supposed to get fresh charge air fuel mixture during intake stroke when piston starts traveling from TDC to BDC and intake valve opens. Instead of what we are getting, the combustion gas that is there in the clearance volume from the previous cycle will rush towards the throttle valve, and that movement of the combustion gas will try to block the intake manifold. Now, further movement of the piston from TDC towards BDC will try to now induct that combustion gas along with the fresh charge. Now, what is happening, since the combustion product is blocking the path, so the amount which we are supposed to get during the movement of the piston from TDC to BDC we won't get. On the top of that, the combustion product, the residue that is there from the previous cycle, we will try to mix with the fresh charge, and it will try to I mean what will get, that the mixture will be much more linear. So, the charge which we are supplying in the intake stroke, during the intake stroke, will be mixed by the residue gas that is there, and as a result charge will be linear. On the top of that, the movement of the the combustion gases from the clearance volume will rush towards the throttle valve because of this pressure difference, and that will try to create blockage of the incoming charge, and as a result we will get less amount of fresh charge. To reduce the possibility, so our objective is only to start up the engine, not to supply in load. Even then, the fuel air ratio that will be supplied won't be able to keep the engine in the startup mode. So, what we need to do, we need to supply more amount of fuel air mixture, essentially to overcome these two effects, that is what is known as, very important, that dilution of fresh charge, that is fuel air mixture, or by the combustion gases. So, that means the combustion gases from the previous cycle will definitely dilute the fresh charge. Not only that, it will try to create obstacle for the fresh charge which is going to come in the next first stroke of the next cycle, and those will be there. Now, to prevent, although we are not supplying any load from the engine, but even to keep the engine in starting condition, we need to supply more fuel, I can say fuel air ratio which is higher than the stoichiometric air fuel ratio. So, to not to prevent, we cannot prevent dilution of the fresh charge by the combustion gases. Because of the dilution of the fresh charge by the combustion gases, as well as the resistance offered by the combustion gases for the oncoming resistance provided by the combustion gases to the fresh charge which is coming during the intake stroke from the carburetor into the cylinder, will lean the mixture, and to run the engine during the condition we need to enrich the fuel air mixture, and that is why we have seen from the previous figure that the fuel air ratio that will be supplied even during the idling zone will be higher, and this is the case. So, that is what we have discussed. Cruising zone we need not to discuss, that is the most economic zone of the operation, and where we need to supply only the stoichiometric air fuel ratio. But again, if we look at the power zone, where we can see that the air fuel ratio, that will be air fuel or fuel air ratio, that will be supplied to the engine cylinder by the carburetor will be higher than the stoichiometric. And why we need to supply again higher than the stoichiometric, that we have discussed, that we are trying to maximize the power output. So, it is quite common that we should supply, rather we need to supply more input energy, and that input energy means more amount of fuel, and of course to have a complete combustion we need to supply more amount of air. Another reason is that when we talk about maximum power, that means mass flow rate of the combustion gas will be increased. So, when we are talking about the power zone, that means engine should run, rather engine should provide maximum power output. If we need to supply more power, rather if we need to get more power from the engine, then that means the mass flow rate of the combustion gases will be increased. If the mass flow rate of the combustion gases is increased, then the combustion gases, when they are leaving the exhaust valve and also the exhaust manifolds, exhaust manifold, these two parts, exhaust valve as well as the exhaust manifold, these two parts are very important part, because with the increased mass flow rate, the temperature of these two parts will be higher. So, when that means to maximize the power output, we need to increase the mass flow rate of the combustion gases, and when the rather higher amount of combustion gases are leaving through the exhaust manifold, then exhaust valve and exhaust manifold temperature will be higher, and to prevent the breakage of these two parts, we need to supply more amount of fuel and air, so that we are enriching. That means the amount of fuel air that is being supplied will try to reduce the flame temperature, will reduce the temperature of these two parts, so that will reduce the flame's temperature, so that the combustion gases temperature will be reduced and these two parts can be saved. So, the first one is essentially since we are looking for higher power output, we have to maximize, that means the engine, we need to maximize the power output, and for that we need to supply more input energy, more power input, that means input energy should be more, and for that we need to supply more fuel, that is quite obvious. On the top of that, what we have discussed, that when we are thinking about doubling the power output or increasing the 1.5 or 1.7 times of the power output from the engine from its design load, then of course the mass flow rate of the combustion gases will be increased, and when the mass flow rate of the combustion products is increased, then the temperature of the exhaust manifold and the intake valve will be increased, and these two parts may break. Now, question is to prevent them from the failure, this high temperature cracking, we need to enrich the fuel air ratio, so that the flame temperature can be reduced and these two parts can be saved out from the excessive heating. So, the requirement of fuel air ratio, high fuel air ratio, rather the fuel air ratio which is higher than the stoichiometric one, we have explained. So, why we need to supply more amount of fuel air ratio than the stoichiometric one during idling zone and power zone, we have explained, and cruising zone, of course we need not to explain anything, because engine should run most of the time during this zone, and this is the most economic zone of operation, and of course engine is running in the at a fuel air ratio which is the stoichiometric one. So, to summarize today's discussion, we have discussed about different zones of engine operation, and that is very important, because engine should be able to supply power from depending upon the load, now depending upon the requirement of course, and when we trying to when the engine is supplying load depending upon the requirement, of course the fuel air ratio will be increased, and we have depending upon the power, depending upon the load supplied by the engine, we can classify engine operation into three different parts that we have schematically depicted over here, and also we have tried to understand that what will be the amount of air fuel ratio, whether we need to supply the stoichiometric air fuel ratio or the fuel air ratio that will be supplied to the engine should be higher than the stoichiometric one, that also we have discussed during three different zones of operation. So, with this I stop my discussion today, and we will continue my discussion in the next class. Thank you.